Question 3. Antonio arrives at a train station at a random point in time. The trains to the desired destination are scheduled to depart at 12-minute intervals. Part A. Assume that Antonio gets on the next train. And Part 1. Suggest an appropriate distribution to model his waiting time and give the parameters. Keywords in this question are random. He arrives at the train station at a random point in time. He can arrive at the station at any time at all. And we're looking for a model that looks at his waiting times. If the trains depart every 12 minutes, his waiting time can be anything between 0 and 12. And this time is equally likely. So this will be a uniform distribution, a constant distribution. So X is a uniform distribution defined over the interval 0 to 12 minutes. Part 2, we have to state the mean and the variance of this distribution. So we can do this by looking this up in the formula booklet. The formula booklet tells us if the interval is over the interval a and b, the PDF is 1 over b minus a, the mean is a half a plus b, the variance is 1/12 b minus a all squared. X was uniform over the interval 0 to 12. So A is equal to 0 and B is equal to 12. So the mean is half of 0 plus 12, which is 6. The variance is 1/12 of 12 minus 0 squared, which is 12. So the mean is 6 and the variance is 12. Part 3 is what is an assumption you have made in suggesting this distribution. This all hinges on the fact that all the trains will run exactly to time, and so then the waiting time can be calculated as a uniform distribution, but the trains must be running exactly on time. Part B. Now assume that the probability that Antonio misses the next available train because he is distracted by smartphone is 0.12. If he misses the next available train, he is sure to get on the one after that. Find the probability that he waits between 9 and 19 minutes. So we've got to think about this very carefully because it's fairly complex. The first thing to consider is he is distracted by his smartphone, and the probability of that is 0.12. So he's either distracted by his smartphone or he's not. So we could look at this in terms of a tree diagram to start with. So he is distracted and then waits between 9 and 19 minutes, or not distracted and waits between 9 and 19 minutes. So if he's distracted, the probability is 0.12. If he is not distracted, the probability is 0.88. If he is distracted, he misses the train. And if he is not distracted, he will catch the first train. If he misses the first train, he is on the second train, so he has not got a probability between 9 and 19, but it is between 12 and 19. If he was not distracted, he catches the first train, and that means his time is not waiting between 9 and 19, it's anywhere between 9 and 12 because he got on the first train. The probability that it takes between 12 and 19, well, we're following a uniform distribution, so that is a gap of 7, but it could have been anything from 12 to 24 for the second train, so it's 7 out of 12. The probability his time is between 9 and 12 is a gap of 3, so it's 3 out of the 12 minutes available. So the probability he was distracted and his time was between 9 and 19 will be found by doing 0.12 times 7/12, which is 0.07. Or he is not distracted, and if his time is between 9 and 19, we want to work out probability he is weighted, which is 3/12 times the 0.88, so 0.88 times 3/12 is 0.22. We then need to say the probability that his time is between the 9 and 19 must be the first probability 0.07 plus the second probability 0.22. And 0.07 plus 0.22 is 0.29, the required probability.
For B part 2, we're asked for the probability that he gets on the first train, given that he's waiting between 9 and 19 minutes. Now, this is the same as saying the probability that his waiting time is between 9 and 12 divided by the probability that the waiting time was between 9 and 19. As a note, notice that the probability of x being between 9 and 12 intersection with x being between 9 and 19 is the same as the probability that x was between 9 and 12. So if you were going to use the conditional formula for this part, just make that 9 a bit better, then that's why we only have to put that on the top. Anyway, we have the numbers for that. The probability that's between 9 and 12 is 0.22. And the probability between 9 and 19 is 0.29. So that gives us 22 over 29, which is 0.7586 as a decimal. I want to show you another question using a tree diagram, and this one leads to a conditional probability as well. With this one, we're looking at a disease and a test, so it's quite pertinent at the moment. May not be if you're watching this a few years down the line, hopefully not, but at the moment it is. And I'm going to represent having a disease by a sad face, and it's known that 5% of the population have this disease and 95% don't. Now, I'm not suggesting that this smiley face means that the 95% don't care about the 5%, it's just in relation to whether they have the disease or not, and it's a bilingual symbol. So, we have a test for this disease, and we want to find out the percentage of positive test results that are false positives. So, if we make a tree diagram, then we can have the first branching is whether you have the disease or not. So this is the have the disease and this is the not have the disease, and we know that it's 5%, so we can put 0.05 there and we can put 0.95 there. Now we also know that if somebody has the disease, then this test gives a positive reading with 98% accuracy. So the test result will be positive 0.98 of the time and negative 0.02 of the time. But we also know that the test, when tested on someone who hasn't got the disease, its accuracy is 99%. So that means it will correctly give a negative reading with a probability of 0.99, and it will give a false positive reading with a probability of 0.01. So, if we want to know the probability of a false positive, then we need to know the probabilities of positives in the two cases. So we need to know the percentage of tests that are positive tests on those with the disease. So that's going to be 0.98 times 0.05. And we need to know the positive tests on those who don't have the disease. So that's going to be 0.95 times 0.01. So the first one gives us 0.049 and the second one gives us 0.0095. Now we could work out these other two probabilities, these two here, but we don't care about them for the question we're asking. What we do know is if we did work out those question marks and then added up the four probabilities, they'd all add up to 1. And that would be the sample space for finding out correct positives, which is the first branch, this one here, incorrect negatives, incorrect positives, and correct negatives. Now what we want to know about is what proportion of positives are false positives. So we now have a new sample space which involves just these two. And so within that space, false positives are 0.0095, and overall there are 0.049 plus 0.0095, and when we pop that into the calculator, that gives us 19 over 117, which as a percentage is about 16.2%. Now that tells us that this test, although it's 98% accurate on those with the disease and 99% accurate on those without the disease, gives a false positive 16.2% of the time. And this is a good example of where probability sometimes makes you think.